At what speed and on what course should an airplane fly in order to travel exactly north for a distance of 200 kilometers in a time of 2 hours, if during the flight a northwest wind is blowing at an angle of 30 degrees to the meridian with a speed of 27 kilometers per hour? So our plane goes north like this. The wind blows like this. So the direction of the velocity of the plane that it pushes off from the air has to be kind of like this. Let's have a look on this picture. Here we have three main vectors. The red one, green one, and purple one. The red vector is the velocity of the wind. The green vector is the velocity of the plane relative to air. And the purple one, this is the sum of two. This is the velocity of the plane relative to Earth. The velocity of the plane relative to air is directed at some angle θ2 that we are going to find. And also we are going to find this velocity of the plane relative to air itself. So the first obvious idea is that the horizontal component of this velocity of the plane relative to air, this one, must be equal to the horizontal component of the velocity of the wind. So in this case, the plane doesn't go either west or east. Just goes north, exactly north. Let's have a look on the solution. The first obvious step is that the velocity of the plane relative to Earth equals the distance that it has to cover divided by time. The second step is that the velocity of the plane relative to air x, the horizontal component of this velocity, equals the horizontal component of the velocity of the wind that we just discussed. And the horizontal component of the velocity of the wind equals the velocity of the wind times sine of θ1, because if we consider this triangle, we can notice that the horizontal component of the velocity of the wind is the opposite leg in this triangle, and the whole velocity of the wind is the hypotenuse. So the hypotenuse times sine of θ1 equals the opposite leg, which means it equals the horizontal component of the speed of the wind. The third step is that the whole velocity of the plane relative to Earth equals the vertical velocity of the wind plus the vertical velocity of the plane relative to air. We just discussed it as well. This vector plus this vector equals the purple one, the whole velocity of the plane relative to Earth. And then we can just rewrite these velocities as the velocity of the wind times cosine of θ1 and the velocity of the plane relative to air times cosine θ2 by the same logic. In these triangles, these vectors, they are adjacent. So we have to multiply hypotenuse by cosine of the angle to get the adjacent leg. Then we can derive the tan of θ2 as the ratio of the horizontal component of the velocity of the plane relative to x, this vector, to the vertical component of this velocity plane area y. So we will get the tan of θ2. Let's rewrite them. The horizontal component of the velocity of the plane relative to air also equals the horizontal component of the velocity of the wind. And the velocity of the plane relative to Earth equals L divided by T. Let's substitute these things, and we can see that we have everything. We have velocity of the wind, we have θ1, we have L, we have T. So we already can calculate the tan of θ2. And of course, after this, we also can calculate θ2 itself as arctan of this ratio. When you will get θ2, you also can calculate the velocity of the plane relative to air as the ratio of the velocity of the plane relative to air x, the horizontal component, to sine of theta 2. And you will already know the sine of theta 2. I mean, you will already know the theta 2. Can you calculate theta 2 and the velocity of the plane relative to air and leave your answer in the comments?